Hello, in this video I will introduce ROC and AUC, which stand for Area Under the Curve. Sometimes in classification tasks we need to decide what is the optimal classification threshold for our business problem and what is the classification threshold that fit our prediction the most. How to compare performances of different binary classification models. That is what ROC and AUC is coming for. To give us the context, let's have a look to the sample data. Here I have logistic regression problem. Here we are looking for people who potentially will finish the race, that is positive case, and for people who potentially will not finish the race based on their walk distance. This selected feature is plotted on the x-axis. I'm using this crazy example just for demonstrating purposes. We can see that the green data points mapping those who actually finish the race and the red data points mapping those who actually not finish the race. These data points here are not predictions still, they are actual values in this context. Again, the walk distance in kilometers are plotted on the x-axis. We could easily fit here a logistic regression curve. As you know, it is Sigmoid curve used for making binary predictions. This curve will help to model to predict which person is going to finish the race and which person is not going to finish the race, depending on how much distance he or she has walked so far. On this plot, y-axis is probability to finish the race. So this is a scale that goes all the way from those who did not finish the race to those ones who finished the race across the walked distance for every single person. So, if you put someone in the scale here at 8 kilometers, this person obviously doing pretty well. We can map it up to the logistic regression curve and then check the probability on y-axis. The result of this is given person has a big chances to finish the race, approximately about 95 or almost 100%. Now, let's put someone a little bit further down, let's say between 4 and 5 kilometers. If we map it to the logistic regression curve and check the probability on y-axis, we find that this person has lower chance to finish the race with probability around 25%. So far, we couldn't tell if these two persons will finish the race or not with no having any classification threshold, which will tell us if specific person will going above the line, that means positive case, or will go below the line, that means negative case. This is how binary classification works. We must use some kind of cutoff threshold on y-axis for our prediction. Let's draw it at 50% firstly. The main question is what is the right place to draw this line. Depending on what the business problem is, we are actually trying to solve the data problem, keeping in mind how to move this line. We can move the classification threshold up by increasing the specificity. Specificity is the number of correct positive out of the actual positive result. In this scenario, we rather miss out people who finish the race and more focusing ones who not finish the race. What about if we move classification threshold line down? Here we increasing the sensitivity, which is the number of correct negative out of the actual negative result. In this scenario, it is very important for us to have everybody who finished the race is predicted as finished. For example, if we have fraud detection case, we should move the cutoff line down to be sure that you got all positive prediction made. For medicine diagnosis, the same, we want to correctly classify those who has diseases. So, as you can see, the classification threshold line take an important role from the business perspective. Because of these reasons, we always should find the balance between specificity and sensitivity. The question we have to how to draw this line, where the threshold make the most sense. To answer to this, we have to answer what do we want the model to actually show. Do we want to have a high sensitivity or have high specificity? ROC will have to do it. Let's go back and consider this to be our test data. We know these data points are correct because they have been labeled. It is a supervised learning situation and we know that these people at the top, those 5 green data points, actually finished the race, and we know that these people at the bottom, those 5 red data points, actually did not finish the race. So we can use this data to evaluate how good is our model, which is that line, prediction threshold, and figuring out where our threshold line should be. We will do it by introducing a simple confusion matrix. First of all, let's put our cutoff line super low. You can see it as the dashed horizontal line. If you carefully check where the vertical dotted line crosses logistic regression curve and then split the areas to what is above this line and what is below this line, you can investigate that. We have on the right side a predicted as possibly will finish the race, and everything on the left hand side are classified as ones who possibly will not finish the race. So we have got some classification that we can fill into confusion matrix. First of all, let's have a look at true positives. Our true positives are individuals that the model has predicted to finish the race and that once we actually know that finish the race. We can see that there are 5 of them. In fact, all 5 of that people that finished the race have been correctly predicted. So we have true positives of 5. Excellent start. Now, let's go and have a look into our true negatives. Of all negatives, we have 5 of them. 3 of them are to the left of our cutoff line. So those 3 are true negatives. They actually did not finish the race and predicted correctly. We put 3 in our confusion matrix. How many did the model say do they finish the race? In fact, they don't. If you have a look at actuals who did finish the race, we have 5 red data points at the bottom. 2 of them are to the right hand side of our cutoff point. So 2 of them have been identified as going to finish the race. This is our false positives. Write this number into the confusion matrix. Finally, there are no false negatives. There are nobody that has been predicted as not finish the race who actually finished the race. So we got 0 here. Now let's move line up a little, around halfway of y-axis. You can see now that our cutoff point moves a bit and we got sort of balance between 2 sides. We have true positive of 4. We have true negatives as 3. In both cases we have person who has been predicted incorrectly. We have 2 persons who did not finish the race but predicted as they were. This is a false positive. And also, we have 1 person who actually finished the race but predicted as not finished. This is a false negative. Now let's move the line up again. Now we are much closer to the positive side, to person who actually finished the race. If you look at true positives, only 3 persons who actually finished the race being correctly predicted as finished the race. And 4 out of all 5 are predicted correctly as ones who did not finish the race as true negatives. Then we have 2 people who are the false negatives. And then we have 1 false positive. I suppose you got an idea how to find these values on confusion matrix. If yes, go ahead. So now we have 3 confusion matrices. What do we do with this? How do we figure out where the best point for cutoff line lies with all the data we have? One way, I can calculate many and many confusion matrices to find the best position, but it is a tiring and wasteful way. So what we are going to do? It is a time to talk about ROC and AUC. By talking about ROC and AUC, we start with the simple graph that we are going to complete in this last part of the video. On the y-axis we have true positive rate, which is the same as sensitivity, while on the x-axis we have false positive rate, which is actually the same as 1 minus specificity. In order to calculate true positive rate and false positive rate for each confusion matrix, we are having formulas that we will use in this part of this video. True positive rate is equal to true positive dividing by true positive plus false negatives. And false positive rate is equal to false positive dividing by true negative plus false positive. Here is the first confusion matrix that we have calculated just a few minutes ago. First of all, let's calculate sensitivity for this confusion matrix. We have true positive as 5 and false negative as 0. 5 dividing by 5 plus 0, and as a result of this, our true positive rate equal to 1. Now, let's take a look at false positive rate. For this, we have false positive equal to and true negative equal 3. 2 over 3 plus 2, and we got our false positive rate is 0.4. So, for this confusion matrix, we have plot a point on our graph where true positive rate is 1 and false positive rate is 0.4. Let's draw this point on the graph here. And now, let's do it one more time for the last confusion matrix we have. Okay, let's calculate true positive rate and false positive rate in the same way we did for the first confusion matrix. Take the needed values from confusion matrix and quickly calculate. For true positive rate we get 0.8 and for false positive rate we get 0.4. Let's draw this point on the graph here. And now, let's do it one more time for the last confusion matrix we have. As we remember, prediction threshold line for this scenario was much closer to ones who finished the race, in other words, to positive side. So, do the calculation quickly, calculating true positive rate. True positive is 3, false negative is 2. 3 dividing by 3 plus 2 and our true positive rate is 0.6. Now do the calculation for false positive rate. False positive is 1, true negative is 4, and our false positive rate is 0.2. We have one more point on our graph right here. Now, if we were to carry on doing this and get more confusion matrices, calculate more true positive rate, more false positive rate, then it will probably look something like this with all our points mapped along the graph. And we have drawn a line along these points. That is called receiver operating characteristics. A simplified name is ROC. In this line we have to find points at which the line significantly changes its direction. In our case, we have highlighted a point that represents the best model if we care about to have the maximum sensitivity. In this scenario, almost everything will be shown as positive. But there is not a point to do it because we are not going to be able to classify any data. What we want to do is to balance classification and sensitivity. These ones represent the best model that has the maximum specificity. So, if specificity is what we are looking for, but we also want to be able to classify our data, then this is a model that we would choose. We can see those because we have plotted them on the receiver operating characteristic ROC line. And for both cases, we are looking for the corner point on the graph where the line changes from being completely one-sided to other. That is why we looked at both sides. This is why ROC curve is useful for finding the best separation of our classes in our model, but also then which one is going to work for us best from specificity or sensitivity point of view. Now, for the understanding of full picture, we have quickly discussed AUC, which stands for area under the curve. This area under the curves represent generally how well this model overall is good at separating between different classes. The larger area under the curve is better. In real world, we are trying to maximize that as much as possible. So, if we have alternative models, maybe built by alternative algorithms, we could plot all of the ROC graphs on the top of each other and figure out which has the largest area under the curve. One model has a larger area under the curve while other has smaller area. As we have discussed, we want to select the best model which have the largest area under the curve. In our example, we see that we should pick up this one on the left, and then find the prediction threshold that classifies our data the best based on the business problem. So in overall, ROC helps us to find an optimal prediction threshold in algorithm, while AUC helps us to find the best model among different ones with the highest AUC on ROC plot. That is all for this video. I hope that it was useful for you and never stop learning. See you on the next videos. Bye bye.